In many applications, such as in computer chips or semiconductor lasers, the crystals used must have no or only very few dislocations. A fast, non-destructive method of examination is needed to verify this condition: X-ray topography. Crystals in an atom constitute a three-dimensional periodic arrangement. When X-ray beams impinge upon such a lattice, they are diffracted, leaving the crystal in specific directions at different intensities. The angles and intensities of these diffracted beams allow the arrangement of atoms, that is to say, the idealized structure, to be computed. This structure provides information about defects of the kind occurring in a real crystal. Thus, atoms may be missing or may be located in a wrong lattice position. When such point defects are arranged along lines of the crystal, dislocations are produced. When a region of this type is recorded on a film sensitive to X-rays, a dislocation appears as a bright or dark line. The number and distribution of these dislocations are a measure of the quality of a crystal. Synchrotron radiation is characterized by its broad spectrum of wavelengths of high intensity. This broad spectrum excites a particularly large number of diffraction reflections, which constitute a symmetrical pattern, the Lower pattern. This diffraction pattern is varied by turning the crystal on the goniometer. However, it is not only the diffraction pattern which provides information about a crystal. Also, the internal structure of each single diffraction reflection is of special interest. High-resolution X-ray films are needed to record the fine structure of the diffraction reflection. After brief exposure, the film can be taken out and developed. As a consequence of the coherent synchrotron radiation, each diffraction reflection includes a topogram which now can be evaluated under the light microscope. This topogram contains information about the type, number, and distribution of dislocations. The great added benefit of this method lies in the large number of topograms obtained from the same sampling site in one exposure step without any sophisticated adjustment. Supplementary information is obtained by changing the geometries of the incident and the diffracted beams. The design of anchor allows quick changes among these geometries: transmission geometry, back reflection geometry, and glancing incidence geometry. The topographic measuring station is an installation for use whenever the structural properties and the quality of crystals are to be determined in fundamental research to improve materials in crystal growing and in the investigation of thin epitaxial layers or solid-state devices.